sequence is a list of things in grade 11. The first kind of sequence you looked at was an arithmetic sequence, where you just add the same number every single time to get the next one. And you had some formulas from grade 11 for arithmetic sequences. We call the same amount that you're adding each time a common difference. In formulas, they usually use the letter D for common difference. So here's an example. What am I adding each time? I'm adding 3. It's called a common difference because you pick randomly any 2 in a row. I picked 11 and 8. And if I subtract 11 minus 8, I get 3. Can you see that if I randomly would have picked any 2 in a row and I subtract them, move this over, I got 3. What about the first 2? I get 3. That's why they call it common difference, because it's common all the way through. You're always adding 3. It's like, ooh, don't know what the next one is. But if I subtracted them, it would be 3. Okay, I do know the next one's 4. Even though it's not real. So it has that pattern going over and over again. The next type of sequences you learned about were geometric sequences, where you had a common ratio. Pick randomly any 2. A ratio is a fraction. If I divide those 2, I get 2. And it doesn't matter which 2 I pick in a row, the division is the same. Which could be helpful in solving, because what happens when you do questions like this is sometimes it's really easy to see the common difference and the common ratio. Because the mental math is like, oh, we're doubling. You knew R was 2 right away. Okay? If I don't tell you what we're doing, yeah, really not very nice. What's the middle number? This one I'm going to tell you that I'm multiplying. In other words, I put a variable in there. What is x? What's the problem is I don't know what I'm multiplying by. If I told you were multiplying by blah, 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 like 7, you'd be like, no problem. This will be 14. Unfortunately, 14 times 7 is not 31. So it's not 7. But how do we use this idea of a common ratio to solve this? Even though I don't know what R is, if I pick any 2 in a row and divide them, that would tell me what R is. Would you agree that if I pick the first 2, my R would be x divided by 2? If I pick the next 2, my R would be 31 divided by x. Are those R's different? No, they are common. Does it make sense that the x divided by 2 has to equal the 31 divided by x? And so if I just multiply this out, I get x squared. Wait, it was probably on the tip of your tongue that middle number was plus or minus the square root of 62. Yeah, I know you're probably, I had plus or minus the square root of 61. I was so close. But we can use, so sometimes an easy idea like the common ratio can come up in a more difficult question, which makes you have to go back to the basic understanding. The basic understanding is if I take any 2 in a row and I divide, I get my common R. If I have more than 2 of them, I can write that out 2 different ways. The first 2 divide or the second 2. And that can help me find that value in between. Okay. The numbers in a sequence are called terms, and we usually do like a T with a little one. Sometimes you'll see textbooks switching the T to A. I like T because T makes me think of term. A, I guess they just first letter in the alphabet. And then your general term, your TN or AN, and maybe your textbook this year is using AN when it says it. That's a formula. So with an arithmetic one, we had the following formula. And you can create this formula for both of these quite easily. So again, now that you have to memorize formulas, method one of memorizing formulas is to look at a formula and just memorize it directly, devoid of any context. You have to have a really good memory, but you can remember random things that way. But sometimes that's hard on your brain because it's devoid of meaning. If you can create meaning for these formulas, they become easier to remember. Take, for example, I'll start with the general term of an arithmetic one. We'll start with 5. We will add, not too big of a number, 3. How about 5, 8, 11, 14? Are you okay with that? Do you notice that each time I'm adding 3? Obviously, it's arithmetic. So to come up with a formula, what we're going to do, term 1, term 2, term 3, term 4, term 5, is break down how we can get from term 1 to term 5. Or term 4. We can pick whichever one we'd like. And this is going to help me remember the formula. If I want to get term 5, does it make sense that I could start with my 5, and then I'm jumping 1, 2, 3, 4. I would have to add 3 4 times to get to term 5. And I do a basic, easy example, and now I take my brain and go crazy, abstract, and general. Could I use this pattern to find any term? Yes. What did I do in my pattern? I started with my first term. Then I realized I was adding the same thing every time. The thing that I'm adding the same thing every time is my common difference. And when I wanted to find the fifth one, I added three times. If I wanted to find the fourth one, I'd add it 3 times. If I want to find the nth one, I'd have to add it n minus 1 times. So I take a specific example, recognize what's happening, and then I'm like, I can make this formula. For me, in my brain, I have only so many random things I can remember. I don't know. I'm trying to extend it, but it seems like it's pretty set in how many random weird things I remember. And as soon as I remember one new random weird thing, like I learned all of your names, you guys are all random weird things. Right? Because names are like random and weird. Someone just picks something for you. I don't look at you and go, oh yes, I can see in the features of your earlobes, you're definitely a cat, right? There's no formula for what your first name is. So those are random weird things. And as soon as I remember all of your names, there's random weird things probably in the past that just like, my brain just sort of like sweeps away and gets rid of. So if you can create things like this, where you're like, I don't have to remember this, because I can always make it. And if you can always make it, the more times you make it in your brain, all of a sudden it just becomes one of those things you just know. Right? Your parents are around in weird things. You know their name. You're never going to forget them. They're now in set in stone kind of stuff because you've used it so many times. Same thing, geometric. Could we do this same pattern? Let's say I'm multiplying by 2 and I'm starting with 7. Term 1, term 2, term 3, term 4. I'm multiplying by 2. Start with 7, multiply by 2. I didn't want to have a big number. So if I wanted to find term 4, if I want to find term 4, I could take term 1 and I've multiplied by 2 3 times to get there. How could I start with term 1 and get to term 4? Term 1, I have doubled and doubled and doubled, so 2 3 times. Then if I take that and say, if I want to find any one, I would start with 7, which happens to be term 1. I'm multiplying by 2, which happens to be my common ratio. And it's 1 less and minus 1. And we have our formula for geometric sequences as well. Super cool. I like it when, and not all formulas work out nicely like this, that you can figure them out easily again. But if you do, that helps you remember. So we went and we looked in different textbooks all over the place for different ways these things could be written. Here they added squiggle brackets around. Does it make it any harder? No. Did you need those? Probably not. But what's term 1? Plug it in. Minus 2. What's term 2? Do 1. So you could just plug things in and find each of these. Can you write down the first 4 for the next one? I'll put up the answer in a second. Did you get 2, -1, 2/3, and -1/2? I think if I gave you those first 4 terms, coming up with the formula would have been hard. I think if I gave it to you this way, okay. Sometimes simplification, I just don't know what. If I would have given you those numbers in green, do you see that the top number stayed 2? And the bottom numbers went 1, 2, 3, 4. And it changed from positive to negative, positive to negative. So the unsimplified formula form is like really easy to see the pattern. Simplification can sometimes be a terrible thing for seeing patterns. So I personally sometimes like things unsimplified. A sequence that is recursively defined. If you can describe the pattern that's happening from one to the next, that's a recursive formula. If you can find the formula that just finds any term you want, that's an explicit formula. So a recursive formula for an arithmetic sequence would just be like this. If you're adding 3, I say that any term is the previous term plus 3. This would be an arithmetic sequence. It always had, but in a recursive one, you always say something with the previous one to find the next one. It's what your brain does naturally when you're looking for patterns. How do I use the previous one to find the next one? Like the geometric ones? Oh, I keep doubling. What's the problem with recursive formulas? Is if I give you the first 3, and then I say, find the 800th one. You have to find all the ones before. If you're going to use the recursive formula, you have to find all the ones until you get to the 800th one. It's a little bit time consuming. So the actual formula is nice for that. But the recursive formula is when you can see things right away. So here, this is saying, right, the first 5 terms, the first one is 1. You can find any other one you want by taking 4 times the previous one. This formula works when n is bigger than or equal to 2. So if I want to find u1, I can't use the formula. That's why u1 was given to us. But if I want to find the second one, it's going to be 4 times the first one, so it's going to be 4. The third one is going to be 4 times the second one, so it's going to be 16. And so this is a recursive formula for this geometric sequence. Try the next one, write out the first 5 terms. See if you recognize the answers. So U1 and U2 are both 1s. And then the next one is found by adding the 2 previous ones. Did you recognize these numbers? It's a Fibonacci sequence. What is the 800th Fibonacci number? Whew. You'd have to do this a long time, wouldn't you? Or maybe you could look up on the internet. That's probably a good way to do it. ChatGPT would probably know what it is, right? Is there a formula for the Fibonacci numbers? There is. Maybe you'd look that up. I don't have it memorized. Now we have our sum formulas. If we're adding things up, it's called a series. And we are going to be adding up a lot of things this year. Calculus, part of the idea of calculus is you can find an answer by adding a bunch of little parts. Okay? Does anybody here, I'll give you a little sense of what calculus is about. Does anybody know the formula for a blob? So one of the formulas you've memorized, the blob formula? No, it's a little bit problematic. So mathematicians want to find the formula of blob. It's problematic. So they go to estimating. I know the formula of a rectangle. So I could use this big rectangle and get an approximation for blob. What's the problem? Is probably not very accurate. So somebody else says, well, let's not use that big rectangle. Let's make some smaller rectangles. Let's go, ooh, this one here, and I'll make a little one here, and I'll make one here, ooh, and I'll make one here. Oh, this, okay. I make 4 rectangles to estimate my blob. It looks pretty, I'm feeling pretty good about my estimate. I only did I had 5 rectangles there. I mean, I'm a little bit of error here, maybe a little, there's some errors, right? It's not going to be perfect, but it's going to get better. What if I made my rectangles smaller? Would it be more accurate? Yes. If I keep making them smaller and smaller and smaller and smaller, it's going to get more accurate, more accurate, more accurate, more accurate, but then I have to add a whole bunch of things. We're going to do this in calculus. One of the things in calculus is, hey, if I add up a bunch of little rectangles, I could probably get pretty close to the blob formula and figure it out. The problem is I don't want to write out a whole bunch of things in a row, so we get a summation notation which uses the Greek capital letter sigma, so it's sometimes called sigma notation. And what sigma notation is a way for figuring out sums. Basically, this part, that means sum. This part is the formula. The formula is TK. The first value or starting value of K. And the last number here would be the last value of K. So the way that summation notation works is you see the big sigma, and you say, I'm going to have to add. What are the terms that I'm going to add? Well, here's my formula. I'm going to start with K is 1, so I would start by adding term 1. then we go up by 1 until we get to the last value of k. So the formula says, okay, first you're going to put in 1, then you're going to put in 2, then you're going to put in 3, then you're going to put in 4, then 5, then 6, then 7, and you're going to go all the way until you get to whatever the number is on the top. So I will give you some that we're going to figure out, but that k is our starting value. You could start k starting at 5. And then you go to 6, then 7. You always go up by 1 until you get to the number at the top. So we're going to write out what some of these would look like. If my formula was 1 over k, and I started with k as 1, does it make sense? Your first term would be 1 over 1. And then k becomes 2, then you go plus, because it's a sum, 1 over 2, plus 1 over 3. And then it would keep on going until you get to the last number. In this case, it says n. But sometimes they'll put a number there. Say, go up to 10. So then you do 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4, 1 over 5, 1 over 6, 1 over 7, 1 over 8, 9, and then stop plus 1 over 10. And then you would stop. We often go up to n to create a formula like you could add up to any number you want. And the summation notation, or the sigma notation, is often shorter to write out than all of the terms. And you don't need a dot, dot, dot. Writing them all out is nice and visual, though. Like, I can see the math that's happening on the right-hand side. The left-hand side is almost too condensed that I have to, like, break it out again to think about what's actually happening. But mathematicians like condensed forms, so this summation notation allows us to do it condensed. Second one. Our formula is k factorial. You would start at 1. And it's a sum, so we do, our first one would be 1 factorial, then you're going to go plus, then 2 factorial, then plus 3 factorial, then plus, and keep going until you got to n factorial. So I want you to look at the next two examples, use the formula, write them out, add them up, and see if you get the sum. I'll give you just the answer for the first one. So if you got the answer, you're like, okay, I think I'm getting this idea. I know how to change the sigma notation to numbers. This one's starting at 2. And it has an I instead of a K. Did that throw you off? No. You guys, way too advanced mathematically, but to be thrown off by changing the letter. Like it. We started with 2, then go up, then do 3, then stop when you get to 4. So what I want to point out in this first example is there's a common mistake. The common mistake is that the number at top says you do it 4 times. Okay? Some of you might have made that mistake. The number at top is telling you where you stop for the value. So because I started at 2, I would do 2, then 3, then 4, and stop. I don't go 4 times. I have a value that I stop at. So that's a common misconception, so this example shows that out really well. Here, this time we're starting at -1, then you do 0, then 1, then 2, then 3. -1, then 0, then 1, then 2, then 3. So we end up 5 things this time. Evaluate each one. And we get a -70 in the end. So starting with sigma notation and expanding it out is easier. The next 4 questions give you the sum. Could you write it in sigma notation? So test those next 4 on your own. I'll put the answers up very shortly. All right, sigma notation for the first couple. Did you notice that it was something squared? I just went with k squared and went from 1 to 9. You could make up. I could have used I. And I could have started at 2 and went to 10 and made this my formula. It's more complicated and not recommended, but it works, doesn't it? Doesn't that still start at 1 squared? And when I plug in 10 as the last one, it would get 9 squared? Yeah. But I like this first one obviously a lot better. So there's an obvious one, and then from the obvious one you can make all sorts of convoluted formulas that also work. Oh yeah, I'll show you the other 3 tomorrow. We'll end there.